have been in the business of air pollution control systems since 1938. That's about 80 years now, with over 25,000 installations across the globe and in all Fortune 500 companies. We have developed and perfected several flue gas desulfurization technologies like limestone scrubbing technology, seawater scrubbing technology, magnesium oxide scrubbing technology, and dual alkali scrubbing technology for very high and consistent removal of sulfur dioxide from flue gases. These technology-based flue gas desulfurization packages have been custom engineered and extensively in power plants generating more than 40,000 megawatts of electricity, steel plants, aluminium, copper and glass melters to rid off the gaseous pollutants from the flue gas as per US EPA norms and as per MOEF norms in India.
Ducon, a name to reckon with, drawing on more than 75 years of experience. Power plants, producing nearly 35,000 megawatts of power, are using Ducon's FGD technologies for the removal of sulfur dioxide. Ducon has the entire gamut of technologies for seawater, wet limestone and dry FGD systems. A typical wet limestone FGD system starts with reagent preparation. Ducon has a broad knowledge base and system reference to underwrite the application of material handling systems. Limestone from the mines is brought by trucks or dumpers and unloaded into grizzly hoppers. Crushed limestone is then fed to an intermediate silo of suitable capacity via a belt conveyor or bucket elevator. Limestone from the intermediate silo is fed to a way feeder via a rotary airlock valve. A feeder, typically a belt conveyor, feeds the crushed limestone into a wet ball mill at a preset quantity. The recirculated slurry from the underflow of a hydrocyclone and water is added into the wet ball mill at a metered quantity. A reagent slurry at the uniform and desired concentration is prepared in a wet ball mill. This reagent slurry is then pumped into Ducon's wet limestone FGD absorber. The FGD absorber comprises Ducon's patented venturi rod deck and specially designed high-efficiency spray nozzles. The spray nozzles are arranged in a way that covers the entire cross-section of the absorber and avoids sneakage of flue gas at variable gas flow rates. The untreated flue gas, downstream of the particulate removal system of the boiler, passes through a booster fan. The flue gas then passes through a gas heater and enters the absorber. The quenched, subcooled flue gas rises up in the absorber against the irrigated flow of recirculation slurry in a counter-current manner. The fine droplets of reagent slurry mixes and reacts with the SO2 in the flue gas and undergoes a series of chemical reactions, removing more than 98% SO2 in the flue gas. The saturated clean flue gas then passes through a two-stage mist eliminator, wherein entrained droplets are removed, assuring almost zero carryover of entrained liquid droplets. The clean, reheated gas devoid of entrainment, exits to the atmosphere through a chimney. A small portion of recirculation liquid is taken as a bleed from the absorber sump to the gypsum dewatering system. The gypsum dewatering system comprises a primary hydrocyclone and a vacuum belt filter. The primary hydrocyclone underflow is fed to the vacuum belt filter at a measured quantity. The gypsum cake is formed on the belt filter after removing the liquid content of the bleed. The filtrate from the vacuum belt filter is recirculated back to the FGD system. The washed cake, that is the gypsum, is conveyed to a gypsum storage yard via a belt conveyor for further disposal.